Now let's do some diffraction grating problems. These are actually really fun. They're a little challenging to understand. I know that. Suppose we have a diffraction grating. And you remember a diffraction grating is basically a bunch, it's usually a square or rectangle with a bunch of slits. Now, they're much closer than this in reality. We're going to call D the distance between grooves or slit separation. Now, usually I'll tell you that in 1 centimeter there are 25 slits. All right, so you're going to have to find D is the distance, or 1 centimeter, I actually gave you D, divided by 25 slits. But we're going to have to convert centimeters to meters. All right, 100 centimeters. 100 centimeters is 1 meter. So for this one, this would be 1 divided by 2500, or let's see what it is. This is 4. D is going to be 4 times 10 to the negative 4. It's going to be meters per slit. Okay, that's the hardest part. Now suppose I have a diffraction grating here. That's a distance L from a screen. All right, so here's my screen. All right, if I shine light of a given wavelength through this diffraction grating, I'm going to see a bright spot, a distance y, above the central maximum, and there'll be another one down here, same distance. All right, there'll be a central maximum, and then there'll be another bright spot. All right, and the relationship is dy is ml lambda, where d is the distance between grooves, y is the distance to the first bright spot, m is the order. Now, in A1, the order is always 1. Okay, we always look for the first one. We're not going for other ones. L is the distance from the grating to the screen, and lambda is wavelength of light. Now, if I'm doing double slit, I'm always going to give you the distance between the slits, so that's just D. Let's try some. All right. Miss Jensen loses the specs for a diffraction grating and must recalibrate in order to determine the grating spacings. So I'm looking for the grating spacings. I'm looking for D. She shines a red helium-neon laser with a wavelength of 633 nanometers. So lambda is 633 nanometers. Now you know that is 633 times 10 to the negative 9 meters. You're going to go and do that conversion. 2 bright spots, which are 1.4 meters from the central maximum, fall on the wall that is 4 meters away. Okay, so L is 4 meters. That's distance. 2 bright spots, which are 1.4 meters from the central maximum. So basically, I've got the central maximum, then I have a bright spot, and this is 1.4 meters. So basically, what I'm telling you is the distance to the first bright spot is 1/2 of 1.4 meters, or 0.7 meters. What's the space between the grooves? All right, dy is equal to m, and m is 1 in these cases, m lambda L. So d is m lambda L over y. So it's 1 times the wavelength, which is 633, times 10 to the negative 9. L is 4 meters, divided by y, which is 0.7. Let's see what we get. See if I got my answers right. 633 times 10 to the negative 9 times 4 divided by 0.7 gives me 3.617 times 10 to the negative 6 meters. Let's see. So basically, it tells me if my answer is wrong. All right. This is, yeah, my answer is wrong. Happens. This is 3.617 times 10 to the negative 6 meters. This would be the answer if this were the distance to, 1. Oh well, Miss Jensen makes mistakes all the time. Happens. Using the same diffraction grating, she tries to determine the wavelength of a helium-neon grazer. Okay, you know what we're going to do? We're going to use D as 1.81 times 10 to the negative 6 because that's what we had. 1.81 times 10 to the negative 6 meters per slit. She determines the wavelength of the helium-neon laser, keeping the laser at the same distance, so L is 4 meters. The distance from the central maximum to the first bright fringe, so Y is 1.2 meters. What's wavelength? In this case, M is 1. So dy is m lambda L. So I'm looking for lambda. So lambda is dy divided by ml. D is 1.81 times 10 to the negative 6. Y is 1.2. M is 1. L is 4. So 1.8 times 10 to the negative 6 times 1.2 divided by 1 divided by 4 is 5.43 times 10 to the negative 7 meters. And you'll get really good at this. This is 543 nanometers. Either answer is fine. I don't care. Judy and Earl are sitting under a boardwalk one warm summer evening while the light of a low-pressure sodium vapor, whose wavelength, so I know the wavelength is 589 nanometers, so I know lambda is 589 nanometers, which is 589 times 10 to the negative 9 meters, passes through two cracks in a board, producing fringes of light that are 0.002 meters. Okay, now what we're doing, this is a bright fringe, so Y is 0.002 meters. If the boardwalk is 3 meters above the sand, nope. No, Y. Okay, so L, the distance from the slits to the boardwalk is 3 meters. What's the distance between the cracks? So we're looking for D. So, all right, so dy is m L lambda, and once again, m is pretty much always 1 for us. D is m L lambda divided by y. So it's 1 times 3 times 589 times 10 to the negative 9 divided by y, which is 0.002. All right, going to multiply straight across. 3 times 589 times 10 to the negative 9 is 1.767 times 10 to the negative 6, and then divide through by 0.002. And I get 8.835 times 10 to the negative 4 meters. All right, if the distance were smaller, would the fringes of light on the ground be closer or further? Well, let's look at this. I'm going to put this in a different color. All right, D is ml lambda over y. Okay, if the distance between the cracks were smaller, so the distance between the cracks is, oh, solved it for the wrong thing. Would the fringes of light, so I'm looking for y. So in this case, it's ml lambda over d. If the distance between the cracks were smaller, then the fringes of light, y, would actually be larger. So it'd be farther. All right, two loudspeakers are broadcast the sound of a band tuning it before an outdoor concert. While the band plays an A, whose wavelength, lambda, is 0.733 meters, Brenda walks to the refreshment stand along a line parallel to the speakers. If the speakers are separated, so this is my separation, is 12 meters, and Brenda is 12 meters away, so that's a distance L. How far away must she walk between the loud spots. So basically, we've got two speakers going this way. So this is a double slit. This is L. And we're going to have bright spots here. Okay, so we're looking for Y. All right. M is once again 1. So dy is ml lambda. And we're looking for y. It's ml lambda over d. So it's 1. L is 24. Lambda is 0.733 divided by d, which is 12. So this is 24 times 1 times 0.733 is 17,592. Divide it by 12 gives me 1.466. All right, in an attempt to test the particle nature of matter, Claus Jonsson performs an experiment in 61, which is very similar to Young's double slit. Jonsson sets a beam of electrons to two slits separated. So that's my slit separation. V is 2.00 times 10 to the negative 6 meters onto a fluorescent screen that is 0.2 meters away. The screen is a distance L, 0.200 meters away. Due to their high speed, the electrons behave like waves with a wavelength of lambda is 2.4 times 10 to the negative 11 meters. How far apart were the bright lines formed? All right, we're looking for y, where of course m is 1. So dy is ml lambda. We're looking for y, so y is ml lambda over d. So it's 1 times 0.2 times 2 times 10 to the negative 6 divided by d. Crud, messed up. Mind if I back up? Plugged in the wrong lambda. All right, lambda is 2.4 times 10 to the negative 11 divided by d, which is 2 times 10 to the negative 6. All right, go on and multiply these out. 0.2 times 2.4 times 10 to the negative 11 is 4 times 10 to the negative 12 divided by 2 times 10 to the negative 6 gives me, did I do that right? I did that wrong. This is 4.8. Gives me 2.4 times 10 to the negative 6 meters. All right, now John puts on a pair of diffraction grating glasses, which he bought in a novelty shop, and looks at a mercury vapor lamp that is 0.5 meters away. So that is L. L is 0.5, oh, excuse me, messed up. Imagine that, a teacher making a mistake. L is 5 meters away. He sees a yellow spectrum line, 1.6 meters, 1.16 meters, so that's Y, on either side of a light source. If the diffraction glasses have a slit separation, so D is 2.49 times 10 to the negative 6 meters, what wavelength are we looking at? And again, M is 1. So dy is ml lambda. So lambda is dy divided by ml. So d is 2.49 times 10 to the negative 6. Y is 1.16 divided by 1, and L is 5. Going to multiply your numerator across. 2.49 times 10 to the negative 6 times 1.16 is 2.8884 times 10 to the negative 6. Now 5 times 1 is just 5. So 2.8884 times 10 to the negative 6 divided by 5 is 5.7768 times 10 to the negative 7 meters. You can leave it that way, or you can convert it to nanometers, which is 578 nanometers. Now the last one is a Houston radio station, KKRW, has two transmitters that sit atop a nearby broad building. broadcasting a wave that is 2.14 meters long. This is a wavelength. As Klesha drives down I-10 parallel to the two transmitters at a distance of 100 meters, so L is 100 meters, she hears an increase in signal every 30 meters. All right, so this is Y. How far apart are the two transmitters? We're looking for D. And of course, M is 1. dy is ml lambda. So D is ml lambda divided by Y. So it's 1 times 100 times 214 divided by 30. All right, 100 times 214 divided by 30 gives me 713.3333.